Good morning, mathematicians. Oh, is it? Camera's so bright. I'm not even registering at all. Maybe I should change locations. Holy crap. Is it that smoky here? Well, or is that fog? Can't tell. Probably both. Um, yeah. How's everyone doing? Is it that smoky here? Well, hopefully well. Hello, duck with a monocle. Oh, I didn't plug in my microphone. I've got to get set up so y'all can hear the absolute crystal clear ASMR of my voice. Yeah, and the camera's deep right now. Gotta change my whole setup. I guess we're back to sitting normal here. I just like the other direction because of my plants and my guitar. But yeah, there was a time when I was singing a little song for everyone every day. Maybe I need to get back to that. This first post here on Reddit's kind of funny. Uh, you don't need to be a massive genius to solve that problem. It's just brute force. Yeah, it's got to be like an obsessive. Yeah. Okay, what are we talking about today? Uh, what are we talking about today? Um, I don't know. I don't know. I don't know. uh, can you believe I haven't even had that much coffee yet? Oh, we were doing these heck algebra calculations. You know what? I finished doing them after the stream, and they still give me the same answer. And I still don't understand where I'm going wrong. It's in this paper. So maybe I'll tell you the thing that's confusing me. If I can get things to rearrange properly, yeah. I do wonder. If this is the culprit, but I think not. There's a confusing statement in this paper that basically says that if you take normalized parabolic induction and you look at the module for the affine Hecke algebra that you get, that should be the same, not quite as tensoring affine Hecke algebras. So this is defined as some tensor product. But you should twist by this element of the file group first. And that's what's throwing me off, because when I compute an example of this thing, it doesn't seem like you need to do that. And I think I could be going wrong here somehow. Because I think the point of this is yeah, it's very confusing though. It's very confusing. It seems like you don't need to do this. I think I'm just going to send him an email actually, and show the details of my example and ask for some clarification. The only thing I can imagine is that thing I said at the beginning, that he takes this other convention. So normally I think of the absolute value as giving var pi the value q. So the only thing I can imagine is that maybe this is somehow screwing things up, but I don't think that's the case. Which book would I recommend to a new student who will take abstract algebra course? Fredley or Gallian? Holds that student know basic proof? Yeah, I'm not sure if you can clarify it. So does the student know basic proofs or no? And a new, do you mean like a new undergrad? They'll need to know that to answer the question. I mean, I've never looked at Fredley, so I don't know. I liked Gallian when I first came across it, but Gallian is contentious. There's something that Gallian skips. Oh yeah, Gallian doesn't talk about group actions. And so there's a lot of people that don't like Gallian because of that. Yeah. But I don't know. It depends on the other things I asked. Yeah. I'm very student knows basic proofs and an undergrad student. Well, I'm extremely aloofy pilled. I'm big on Aloofy's book. I think everyone should read it from the get-go. But okay, that's just my opinion. Galleon's a nice book. It is an easy read. I'll give it that. But I'm a religious zealot for Aloofy's book, so that'd be my answer. Spelling Aloofy, Aluffi. The book is called Chapter 0. Yeah. He actually has a new book that covers rings before groups. But I'm guessing... well, yeah, you just said abstract algebra. You didn't say group theory necessarily, so... could be worth checking out his new book. I haven't spent any time with it, so I don't know how it is, but you could go and find out. That newer book is actually intended for undergrad, so it might be a better choice. Yeah. The glare is real, is it? I feel like I don't see that much glare. But what is real is how fuzzy it is outside. By which I mean hard to see. By which I mean I still don't know if it's smoke or if it's fog. Could be either. Gosh, do I want to do this computation, but maybe replacing the norm, the value of the norm with a minus? You're looking through a book I recommended a while ago on perverse sheaves, and some of the diagrams got you dizzy. Yeah, there's definitely some crazy diagrams in there. Yeah, there are some crazy diagrams in there. Yeah, they're nuts. I know exactly what you're talking about. I can't, dig up the page number by heart, but yeah, believe me, I know exactly what you're talking about. Maybe, wait a second. Maybe that is the key to everything. Because if he's writing his norms like that, then these two things change. But this doesn't change. You need my help? Okay, well, ask away. Ask away. What do you need help with? I might lasso this thing down. Well, yeah, you can. Yeah, it's pretty common to write a norm with the double bars, but it is also not uncommon to just write the p-adic norm just like this. Yeah, especially since it's like a p-adic absolute value, and yeah, if you're working in it looks like a little face. Let's make it happier. I don't know. I just started drawing this guy, but but yeah, if it's a p-adic norm, yeah, it's just you wanna make easier notation, right? The problem states let AK be a convergent sequence in Rn. Prove that the sequence of norms in R is convergent, and that okay. AK converges. Let's even give a name to its convergent. We want to prove that this converges, and that the limits are equal. Yeah, I mean, so, yeah, I mean, what is it going to convert? I mean, if A is the thing that it converges to in R, then probably, well, it even tells us in the problem, like the thing that this sequence, we're basically trying to show that this sequence converges to A. Well, what do we need to do to prove that this sequence converges to A? What does that mean? Since all norms are equivalent on a finite dimensional space, probably best to use the soup norm. What? The soup norm? How do you define the soup norm on a finite dimensional vector space? What's the soup norm on R2? Well, quality, I don't know. I mean, it depends on what's already been proved here, because, I mean, one could interpret this statement as asking you to prove, to prove continuity. Well, the sequence, I don't know how else to explain it. You take the first thing in your sequence, right? This is a vector in Rn, and you take its norm and you get a real number. And then the second term in the sequence is you take this second term in Rn and you take its norm, and that's a real number. And so on and so forth. Yep. So like if your sequence was 1 in R3, okay, you already said it makes sense, yeah. Okay, so well, can anyone tell me what's the definition of the limit? Like, what am I trying to show here from definition? We're getting pedagogical. Well, I'm asking partly you, Matthias, but also anyone else that wants to chat. What does it mean for, right? This is the thing, this limit we're trying to prove. What does this mean? What does it mean that the limit as k approaches infinity? You know the epsilon delta definition, but not in English, right? So, I guess in English, it would be for all epsilon greater than 0, there exists an n in the natural numbers such that if k is bigger than n, then the absolute value of the difference of these two things is less than epsilon, right? So this is what we're trying to prove. And what do we have as our assumption? Well, we have our assumption that this that the sequence converges. So this is what we want to show. Meanwhile, we have a very similar assumption that probably we're going to make use of. We got the inverse triangle inequality, probably. I mean, all of analysis is just the triangle inequality. To be as reductive as possible. Oh, I should have. Sorry. I wrote something a little bit silly. This should be the norm of A. This should be the norm of A. So let me. A is a vector in Rn. So this should be. Gosh. too many different bars here. So absolute value of norm of AK minus the absolute value of the norm of A has to be less than epsilon, right? So and maybe I'll put below how we would actually start that proof. So since this is the thing that we're trying to prove, our proof should begin with let epsilon. Maybe I should make even more room because we're going to have to do a bunch of rough work. The proof itself will begin with let epsilon be bigger than 0. And then our next step is going to have to be to choose the n. But we're going to have to do some rough work and go backwards in order to do that. So we have, meanwhile, this assumption here that we're able to make this happen, right? So, yeah, reverse triangle inequality, reverse triangle inequality. Is that what we want here? You can always use a norm where if A is equal to that, then that, right. Yeah, but then, well, I was about to say, but then you have to pick a basis. But you got to do that. You got to do that anyways. Yeah. Yeah, fair. You'd have to prove that all norms are actually equivalent, though. Wow, but that is something you should prove. That's a good thing to prove. Yeah. Oh, but for application to this problem, yeah, you're right, Arad. Yeah, you're right. Yeah, I forget. I don't know. Do I just quote that there's some theorem that does it? I feel like I want to, yeah, play around with this statement. So what could we do here? What could we do? Well, let's try and work backwards from the thing that we're interested in. So I guess we have minus epsilon AK between epsilon. Yeah, what do we have? What do we have for the reverse triangle inequality for like Rn or something? This looks like what I want. Are we allowed to quote this? That's the but I need norms. That's what I need. But mind you, okay, wait a second. So I still, I guess we still do have this, right? Because, what would it be if we applied it here? So, no, not really. Because surely there's one, all nearby vectors have nearby norms. Surely there's got to be a way to do this without being that explicit. Surely there's a way to do it without being that explicit. Yeah, here we go. In the case of a norm vector space, there we go. Nice. Right. Okay. So it is just that. So the absolute value. Okay. So it turns out the absolute value norm AK minus absolute value of norm A is less than or equal to the absolute value. Right. Okay. So that's literally the proof then. That's literally the proof. Yeah. Yeah. So the proof is let me just write it out. So we could say something like, since the limit as k goes to infinity, ak equal to a, we can choose n in the natural numbers such that k bigger than n implies that, which one do we have? Yeah, implies that ak minus a is less than epsilon. Thus, for k bigger than n, by the reverse triangle inequality, the absolute value of the norm of ak minus the norm of a is less than or equal to the absolute value of ak, of the norm of ak minus a, which is less than epsilon. Therefore, thus, by definition, the limit as k goes to infinity of the norm of ak is equal to the norm of a. And we're done. QED. Yeah. Where the analysis is real, but the fun is imaginary. Amazing. Amazing. Yeah. Anyone feel up to showing the Cauchy-Schwarz inequality? You mean just pulling the proof out of my butt, out of thin air? I don't know if I'm up for that. I don't even remember the what the hell is the statement of Cauchy-Schwarz? Cauchy-Schwarz. Yeah, that's embarrassing. Oh yeah, it's this one, right? Oh, yeah. All of my analysis instructors are, they just suddenly a shockwave of pain went out across the planet to all my analysis instructors. Hello, Arya. Welcome back. Yeah, I don't know. I don't want to prove this right now. You know it is fun. But definitely I couldn't prove it right now. Is the it came up on stream like a couple months ago, but there was the what was the classification of knowing when an inner product between a norm and an inner product. That's a fun theorem. Basically when, if you have a norm, if you have an inner product, it gives you a norm. And so to know when your norm comes from an inner product. Quick question. Paul Maurice, come on. You know that's not a quick question. Come on. The Tate module of the multiplicative group GM. No, I can't tell you that. Wait, what even is the Tate module? I know the Tate module of the elliptic curve. Is that the same construction? Maybe we could compute that. Oh, maybe this is doable then. If it's just the exact same definition. Tate module of an abelian group. I kind of want to do that one. But people are asking about all of these other things. I'm not going to prove Borsak Ulam. You got a different one. If I want, let F be a subset. The following equivalent. F is closed. Any convergent sequence. I don't know. Maybe I'll do it. I kind of like this Tate module question, though. Right. Okay, which way are we going to do it, though? I mean, right, are we going to do it with the proper étale cohomology way? So we just... oh, I mean, it says right here. The linear action of the Galois group. Okay, well, let's think. I mean, I just know, like, a naive way of computing it for elliptic curves. But okay, let's think. We'll have gal k bar over k. We've got gm over k. And now how do we do this? Okay, so right, we've got our Galois action on here. And and what do we want to do? We want to compute. We need to take. Well, I'm just thinking about. I'm going purely based off of the. Yeah, we want to compute the p to the n torsion. Wait, so actually, right, we are just computing the p to the n torsion in g to the m. So, oh, I guess, wait a second. We want to do this, over k bar, right? Yeah. So then, well, what is the p torsion in gm? I mean, this is just going to be the pth roots of unity, right? So, like, gm pn should just be the p to the nth roots of unity. I guess it is an algebraically closed field. Yeah, as a group, I mean, as a group, this is just Z mod Pn, right? Is that true? Is this really a field independent thing? No, there's got to be. Come on, there's got to be some assumption on the characteristic here or something. Well, at least everything is morally correct. Yeah, I mean, and now we just take the limit, right? So, right, and now the P Hodge or P sorry, I saw the Hodge-Tate filtrations. I don't even know what a Hodge-Tate filtration is. This is just the limit of these things, which is just the limit of these things, which is just the p-adics, right? But then, yeah, there is this Tate twist thing, right? So fun fact, Tate twists come up a bunch in my research. Technically, there's like a bunch of places where these like perverses I work with should actually be like the Tate twist or something, but we just completely ignore it because we don't really need it. Right. Wait, is this an artifact of tensoring up? Do we need this? It's isomorphic as a ZP module, but not as a Galois representation. Right. Characters Galois group. But is there a reason why it's Z1? Let's see here. Group homomorphism. I mean, well, I guess the thing is, if you want to beef this up to a representation, yeah, I mean, as a module, like, I guess as a module, this is just ZP, but I guess maybe this comes from the fact, like, I know, of course, like, so again, I normally just think about this in the context of the Galois representation of elliptic curve, in which case, to get an honest to God, right, this is just, you just have a Galois representation on ZP. But in order to get an honest to God Galois representation, you then tensor up. You tensor up over Q. So this would give us an action on QP. And then, yeah, I think as Arad said, the reason why we put the 1 there, I guess, is just to tell us what the action is, because I guess I suppose if you just wrote like if this was gal k bar over k, well, no, I don't want to say anything wrong. There are technically 2 notions of Tate module: integral, right, and rationalized, right. What did I see here? Something motivic, something. In terms of motives, the p-adic cyclotomic character is the p-adic realization of the Tate motive. Clarification needed, indeed. Yeah, I mean, I think the 1 there is just to tell you specifically the action, but if K is a field, representation, finite dimensional vector space, Tate twist is 1, It's this tensor product. Yeah. But both ZP1 and the cyclotomic characters are defined directly by roots of unity. So I'm not sure to say except by definition. Yeah. This is kind of weird. The Tate twist of V1. Yeah. I mean, it is kind of just by definition, right? Because it's just telling you. Yeah. Yeah, because your Galois group, I mean, in this, according to the definition on Wikipedia, I mean, for example, you could just take, like, it's because, like, this tensored up Tate module, just to totally pattern match with Wikipedia, it is the trivial representation tensored with, right, just the QP where you're given by this roots of unity action. So yeah, I don't know. Yeah, basically by definition. That was that's a nice mix of problems. We did some basic analysis and we did some Tate module nonsense. I think that makes for a good episode. So maybe we'll leave it there. I don't know. I wanna go hit legs before I got a TA at 10. Someone's got to make some meme of me, like when you need to hit legs at 9, but you gotta teach discrete math at 10. There's a meme there. Perhaps I should meme myself. Oh, something Iwasawa theory. Oh, I've seen this formula before. Ah, it's all coming together. Yeah, okay, I'm gonna call it. So, I guess I'll go prove some stuff about Tate module something, and you guys go prove some stuff about Tate module something. Go compute some Tate modules of some other groups. See what happens. See what you get.